how many people have read Nightfall? Okay. How many people have read anything by Asimov? Science fiction? A book? Okay, good. So what this is some work that I did with a student, Smaran, and he worked for me for a summer. So he stayed in Bombay, and we basically collaborated over the internet. So this is about 3 months of his work with very little contribution from me, except just pointing out the story. So let me first. This is not actually what I do for my living, and I'll let John please tell you that.
And now for something completely different.
So this is from the old Monty Python skits, but this is not what I do, and you might question why I'm doing it. Unfortunately, Arnab had other things to keep himself busy. I guess first there was India's shameful defeat to Australia, and then I think he's been having some fights with VK Singh recently. But what am I doing? Working on something that isn't related to my science. And so in this, I've been actually quite lucky in that I've always been in an academic environment. And as such, being the key thing about being in an academic environment is that you're free to do whatever you want. And that is what academics really means. It's getting a little hard to justify that in today's world, where everyone asks how many people you're going to employ, what is your invention going to do for the common man. But really, academics is all about setting up an environment where people are free to think about whatever they want, and by doing so, you set up an environment where people are not afraid to think of new things. So that's really what academics is all about. And I've been, as I said, fortunate enough to always have been in an environment where I can do what I want. And I have I also am fortunate in that I'm very stubborn and I don't take direction easily. So I've been able to do what I want. So the story itself was written in 1941 by Isaac Asimov when he was about 20 years old. And what I'll do is I'll tell you a little bit about the time, about the golden age of science fiction, a little more about Asimov, and then near the end of the talk, I'll tell you what we actually did. So as I said, the short story was written in 1941 when Asimov was 20 or 21. And it was expanded into a full-length novel in 1990 in collaboration with Robert Silverberg. It's generally considered to be the greatest short story in science fiction, and it was voted as such by the Science Fiction Writers of America. People would ask Asimov later on what he thought of Nightfall, and he resented the question because he always resented the question because he said, I wrote that when I was 20 years old. How is it that in the 30, 40 years since then, I haven't written anything better? Haven't I learned anything over the next few decades? But nevertheless, it was, at the time it came out, it was what really brought Asimov into the limelight. It's what made him a household name, at least in science fiction. The story itself is available online, so those who haven't read it can just search for it, just search for Nightfall. And the short story is actually very short. It's only 3 or 4 pages long. So before I start talking about Nightfall itself, it'll be good to define what science fiction is. And you can never go wrong by appealing to Wikipedia, the source of all knowledge. So what Wikipedia says is that science fiction is a genre of fiction dealing with imaginative content such as futuristic settings, futuristic science and technology, space travel, time travel, faster than light travel, parallel universes, and extraterrestrial life. And so this was the first part of science fiction. This was science fiction in the golden age of science fiction, when Asimov, Arthur Clarke, Robert Heinlein, Silverberg, when all these people were writing. And it's the science fiction that I grew up with people going to other planets, colonies on Jupiter, interstellar battles, all this stuff. More recently, it's become more of the social commentary. A lot of modern science fiction is very dystopian. The Hunger Games, for instance. What will happen in a world gone wrong? Conflict, hunger, etc. And so this is the second part of the definition. It often explores the potential consequences of scientific and other innovations and has been called a literature of ideas. Authors commonly use science fiction as a framework to explore politics, identity, desire, morality, social structure, and other literary themes. Now, it arguably started with Mary Shelley, who wrote Frankenstein in 1818. She, Lord Byron, Percy Shelley, and a bunch of others were in a retreat in Switzerland, and they challenged each other to write a horror story. The one of that's done best is Mary Shelley's Frankenstein. You could argue that science fiction is even earlier. Kepler, for instance, wrote something, I can't remember the title now, but Kepler wrote a science fiction story. You can't really have science fiction without science. So you can't have, it's hard to have science fiction that dates back much earlier than the Industrial Revolution. Now, by the time the late 19th century came around, this was when everyone of culture was interested in science. The early 19th century, Faraday would give lectures to, I think he gave lectures to something like 20,000 people in his life. And people were interested. The Royal Astronomical Society, the Philosophical Society, and so on. And this was when the hard science fiction really came of age, with H.G. Wells and the Time Machine, Jules Verne, From the Earth to the Moon, which is a fascinating story. You have, somewhat presciently, he put a huge cannon in Florida. I think it was a 3-kilometer long cannon, and the Selenonauts were fired from the cannon to the moon, where they met the moon creatures. I've forgotten how he came back, but anyway, he got to the moon. 20,000 leagues under the sea, and so on. Now, in the early part of the 20th century was the space opera. And I'll just let this play. You should all recognize at least the music.
What plaything can you offer me today?
An obscure body in the SK system, Your Majesty. The inhabitants refer to it as the planet Earth.
I like to play with things a while before annihilation. Pathetic Earthlings! Who can save you now?
Strange object imaged in the Imperial vortex.
Remove the Earthwoman. Prepare her for our pleasure.
That was Max von Sydow.
Don't kill him yet, Father. I want him. Go, Flash, go!
That's Timothy Dalton. And of course, the music is by Queen, Freddie Mercury and Queen. And so this was, this movie came much later. This movie was in the 80s. But this really epitomized the science fiction of the early 20th century, the space opera. And the people who started space opera was E.E. Smith, Doc Smith. He wasn't actually a PhD, but everyone called him Doc Smith. Edgar Rice Burroughs with John Carter of Mars. I actually liked the movie. Most people don't seem to have. And Flash Gordon. And this was characterized by what was called, or this showed up in what was called pulp science fiction. And the reason it was called pulp is because this was, a lot of it was in the war era when paper was difficult to get. And so they made the magazines out of recycled paper, out of pulp. And so that's why the whole thing is called pulp science fiction. And the premier editor of the time was Hugo Gernsback, after whom the Hugo Award is named. And he had this magazine, Amazing Stories. So this is a pretty typical cover. You have a helpless woman being carried off by a man with huge muscles. This was space opera. This is what happened. You had you had horrible beasties ready to savage innocent earthlings, and you had heroic heroes out to save the world. And of course, they always did. I don't know if the title is here. Did this madman's mistake lie in his attempt to destroy too many worlds? So that was space opera, opera translated into space. Then came the Campbell era, and this lasted for quite a long time. He was editor of Astounding Science Fiction from 1937 up to 1971. He had lost most of his influence by the 1950s. So, but still, he had a good 20 years on top of the field, and he was the editor at the time when the golden age of science fiction was around. People like Arthur Clarke, and the big three of science fiction were Arthur Clarke, Robert Heinlein, and Isaac Asimov. If you ask some of the others, like Robert Silverberg, he would say that the golden age came a little later, perhaps not the late 1930s, 1940s, but perhaps the 1950s. But this is the generally accepted one. So these are the big three of science fiction. And this is the cover of Astounding Science Fiction when the story Nightfall first came out in 1941, September 1941. Yeah, note the price, 20 cents. That was when you could get a full meal for perhaps 50 cents. Now, Asimov himself was born in Russia, and he said he was born on January 2nd, 1920. But Russia was at a difficult time in those days. It was in the just after the October Revolution. There was civil war, and there were some areas that had switched over to the Gregorian calendar, some areas which were still over on the Julian calendar. So it's not clear whether he was born on January 2nd, 1920 or October, whatever it was, 1919. But he himself always said January 2nd, 1920. His family moved to Brooklyn when he was, I think, about 3 years old or so. And he grew up in Brooklyn, where his family owned a succession of candy stores. At home, they spoke Yiddish. And so Asimov spoke both fluent Yiddish and English. And a lot of his science fiction, especially his short stories, has been clearly influenced by the Yiddish tradition, like as for instance Isaac Singer, Bolshevist Singer. Asimov was a wide reader. He read everything he could. The New York City Library was good, and he would read whatever he could. He like Indian parents, his father wanted him to become a doctor, and so he said that he shouldn't read any fiction. But he told his father that this is science fiction, so as long as it's got science in the title, it must be okay. His father let him get away with that, and he read a lot of science fiction in his youth. He was a typical fanboy. He would write to authors. He would write to John Campbell, write to the editors. And finally, as a result of this writing, he got to meet John Campbell when he was 17 or 18. And that's when he first started publishing, in his late teens. His education was in the New York City public school system. And then when he was ready to go to college, he went to Seth Low Junior College. This college doesn't exist anymore. It was a part of Columbia University, but at this time, before the Second World War, there were quotas in all of the universities. Feynman was also caught up in this. And so because he was Jewish, he couldn't go to the main university. He couldn't go to Columbia University. And so he went to this offshoot, Seth Low Junior College in New York City. Now it's been folded into Columbia, and it's one of the branches of Columbia University. He then went to Columbia for his graduate study, and he got an MA in chemistry and a PhD in biochemistry in 1948. Just before he got his PhD in biochemistry, he had a little crisis of confidence. He wasn't sure if he could write fiction anymore because he'd been spending so much time on his thesis. Graduate students tend to go a little crazy in their last 6 months or 9 months. And so he wrote this story called The Endocrinic Properties of Thiamotilene. And he wrote it in a scientific paper style. So he put in citations, references, and everything else. And he sent it off to John Campbell. And he told John Campbell to publish it under a pseudonym, under a false name, because he was afraid that if his thesis committee saw that he was writing a science fiction story in a scientific manner, the committee might not like it. But as it happened, Campbell he published it under Asimov's own name. And so by the time he went up for his defense, the paper was out already. And what the story was what thiamotilene actually was a substance that worked back in time. So for instance, if you drank wine with this thiamotilene today, you would have a hangover yesterday. So you'd get the hangover before you actually drank it. And he wrote it in such a convincing manner that for months afterwards, people would go to the New York City Library and ask to see copies of those fictitious articles that he had referenced in this main thing. So when he went for his thesis, he stood up there and he answered whatever questions the committee asks. It depends on the committee. Usually committees, by the time you go for your thesis, everyone knows that you've done all the work. And so in principle, there's nothing to be worried about. I've had friends who fainted in their defense. But anyway, he stood up there, and whatever the question was, he answered. So he thought he got through everything fine. Maybe these people just hadn't seen this paper. And then finally, the last question was, so Mr. Asimov, what can you tell us about the endocrinic properties of thiamotilene? And he saw the examiners crack a smile, and he was so nerved up that he burst into hysterical laughter and had to be led out of the examination room. And so from 1942 to 1945, he was working in the Philadelphia Navy Yards. Many scientists were not actually sent out to fight in the war, but they were doing scientific research for the war effort. So Rabbi, for instance, Rabbi was doing work on radar at MIT. Fermi, of course, was working on the atomic pile, and so on. And so these are this is Robert Heinlein, L. Sprague de Camp, and Asimov at the Philadelphia Navy Yards. And I'll talk a little bit more about all of them. They all took something different from their military career. Heinlein, at this time, he was what they call a flaming liberal. And Asimov, perhaps unkindly, said that it was because he had a flaming liberal wife. They got divorced about a year after this, and his next wife was an extreme rightist. And so Heinlein, in his later years, was exceptionally rightist, and you can see this in his novels. His early novels, things like Space Cadet, they're all what you call juvenile fiction. And these are essentially light stories. And those are actually the stories I enjoy more. The later ones, things like Stranger in a Strange Land, they're done in his extreme libertarian phase when he, Starship Troopers, where he believed that everyone has a duty to the state, and unless they fulfill their duty, they don't have any rights as a citizen. Now, this duty, in many cases, for instance, in Starship Troopers, the people who were really extreme citizens, so to speak, were the people in the military. His stories were also set, in many cases, aliens took the place of minorities. And so he believed very strongly in equal rights for everyone. He had some weird ideas which I won't get into, but he basically believed that everyone was equal. L. Sprague de Camp, he had a more cavalier attitude to the military. He got out believing essentially that the military was a place of bureaucratic foul-ups. And Asimov I'll get to in a little bit. Now, of the big three, the one who's not here is Arthur Clarke. He also did a lot of work for the war effort, but of course he was British. And he later spent most of his life in Sri Lanka, where he died. He also spent, I think, a year or 2 years in PRL, where he took a sabbatical. Now, Arthur Clarke was gay, and post-World War II Britain was perhaps not the best place to be gay, as Alan Turing's life shows us. So he lived in Sri Lanka. Now, Asimov had a fairly giant ego. A lot of it was self-deprecatory. It's not so much that he believed that he was better than anyone else. He just liked saying so. And so he and Arthur Clarke, always had this fight. And what Asimov said is that he wrote many books. He wrote over 500 books, many of them fiction, many of them nonfiction. The early stage of his career was fiction, the later part was nonfiction. And so what he would say whenever he met any other science fiction writer, he would also say, okay, you've written a lot of science fiction, but you haven't written as much science fact as I have. And when he would meet someone who wrote a lot of science fact, he would say, well, look, you've written a lot of science fact, but you haven't written any science fiction. Now, Arthur Clarke wrote a lot of both. He wrote a lot of science fiction, and he wrote a lot of science fact. In fact, many of our current ideas, things like geostationary satellites, were first brought up by Clarke. Space elevators was another thing that he brought up. And so he always had this fight with Clarke. Who is the better writer? Everyone else, he could say either he was a better science fiction writer or a better science writer, depending on the context. But as with Clarke, he couldn't say either, because Clarke wrote as much science fiction and as much science fact. So one day while they were both in New York, and they shared a taxi going down Park Avenue. And so they came up with what they called the Asimov-Clarke Treaty of Park Avenue. And what this treaty said is that Asimov would always say he was the second best writer of science fiction, but the best writer of science fact, whereas Arthur Clarke would say that he was the best writer of science fiction and the second best writer of science fact. And so in one of his books, Arthur Clarke writes, in accordance with the terms of the Clarke-Asimov Treaty, the second best science writer dedicates this book to the second best science fiction writer. Both of them had a more complicated relationship with the other of the big three, with Heinlein, because as I said, Heinlein had some very right-wing ideas in his later years. And so Arthur Clarke came to New York to testify, or came to Washington to testify in front of the House committee on the Strategic Defense Initiative. And Clark said, this is a terrible idea. We shouldn't be spending so much money on defense. And then he went to California to stay in Larry Niven's house. And he and Heinlein met there. And Heinlein blasted him. He said, how dare you question the wisdom of the United States? And so for a while they didn't talk. Finally, near the end of their lives, they both reconciled, but never really to the extent that Clark and Asimov were friends. Now, Asimov wrote, as I said, hundreds of books. The exact count is a little difficult to measure because many of his books were anthologized in different places, and so and some of them were under other names. So it's somewhere over 500 books. He was a full professor at Boston University, and in 1958, he found out, or he was making more money off of his writing than out of his teaching. He was making $7,000 a year from his writing and $5,000 a year from his teaching. So by mutual agreement, he was already tenured by then. So by agreement with Boston University, they said you can retain your title as a professor, but we won't pay you a salary, and you focus on your writing. So he lived in New York for his entire life. After the 1950s, he switched over to writing nonfiction rather than science fiction. And he did this partly because he found it to be easier and to pay better. The publishers would pay better for science nonfiction than for science fiction. I have two of his books from the early 70s. I got them in the early 70s when I was, I guess, about 10, 11 years old. And these are a 2-volume book on science. And a really beautiful writing. He covers the entirety of science in 2 volumes at a level that's easily understandable. I still have those books. I meant to bring them, but I forgot. And so you can divide his career into the 2 phases. In the first part of his career, he wrote mostly fiction. In the later part of his career, he wrote nonfiction. And he wrote an amazing amount of nonfiction. I think it was Elsprague de Camp who asked him once, Asimov, how does it feel to know everything? And he said, no, I don't actually have to know everything. I just have to make other people think that I know everything. Amongst the things he wrote were Asimov's Guide to the Bible, Asimov's Guide to History. I mean, he wrote an enormous range of nonfiction. This is his perhaps his most famous picture, one of his most famous pictures, in which he's got those mutton chop whiskers, which were characteristic. He died in 1992, and he died of AIDS brought about from a blood transfusion. His family didn't want people to know because this was the time when AIDS was still in its early stages, and there was still the stigma. So it wasn't until much later that people found out that he had died of AIDS. Now the story itself, Nightfall, it was inspired by a quotation from Ralph Waldo Emerson. And the quotation is, if the stars should appear one night in 1,000 years, how would men believe and adore and preserve for many generations the remembrance of the city of God? So Campbell and Asimov were discussing this in Campbell's office. And remember, this was when Asimov was 20 years old. And Campbell said, if people saw the stars one night in 1,000 years, every other day, so you have a black sky, and in only one night in 1,000 years you see stars, people wouldn't adore God. They would rather go mad. And so he asked Asimov to explore this idea. What would happen if the stars appeared one night in 1,000 years? For many years, Asimov thought that this quotation was, he couldn't find this quotation. And so he wondered if it really existed, but it does. Ralph Waldo Emerson did say that. And so this is when he wrote Nightfall, when he was in 1941. The short story came out, and as I said, it made an immediate impact. This is what made Asimov's name as a writer of science fiction when he was 20 years old. The book, the short story was later adapted into a book with Robert Silverberg, and this is the book, 1991. What we used as the material for our work was actually the book, because it contains a lot more detail than the short story. Now, what my connection with this is, I told you I worked with a student, Smaran, and so we got to some level, and so I said, you should get some experience in writing a paper, so why don't you write a paper on this? And so we wrote a paper, and we put it up on one of our public sites. We put all of our scientific papers on this place called Archive, ARXIV. So it's become a repository for preprints in many different areas of science. And they have a section called Popular Science, I think it's called Popular Physics. And so one of the things that was put up maybe a few months before we put ours up was some work that some students at my alma mater at Johns Hopkins, that they did on the Game of Thrones, which I understand came out, I think the next season came out today. So I actually don't watch Game of Thrones for several reasons. One is that I get confused anytime there's more than 3 characters, and Game of Thrones has lots and lots of characters. And the other thing is that I find it hard to get into a show where the character that you fall in love with dies in some painful way 2 episodes into the series. In fact, I saw a quote once. They said, even though you know it's coming because you read the books, you still hope that this character, that there's a difference in the series. And I see that people sympathize with that. I don't actually know the characters. I understand that one of the least popular characters is still alive because George R.R. Martin likes him. But anyway, I'm sorry. So what these students did is they wrote a paper on the weather of Game of Thrones, of whatever that world is. And I understand, again, I haven't read the books and I haven't seen the show, but I understand the weather is really flaky. So it's summer today, and it's summer for 150 years, and then tomorrow it's winter. And winter for 5 days, and then summer again. There's some weird stuff. So they tried to get a system in which this weather, this climate could come about. So they postulated all sorts of things. They said, could it be because of dragons? The dragons have some effect on the climate. And anyway, you can read it. It's up on this site. Just search for weather on Game of Thrones, and you should be able to find it. And so in that same sense, this is a place where people put these kind of works. People also put April Fool's stories. There was one this last April 1st where if you look at the mass of Pluto, from the time it was discovered, it's been steadily dropping. And so they wanted to find out when the mass of Pluto would become imaginary. It turns out that it's not dropping anymore. Now it's going back up. So it's not a linear drop. It's actually a curve. So this is the kind of stuff that you find here. So I told Smaran, why don't you write it up and let's put it there. And so we did that. And here it is. You can search for it. You'll find it. And then to my surprise, within a few days of us putting this article up, it got onto Wikipedia. So this is my entry into Wikipedia, not for the work I actually do, but for this sort of stuff. And actually, I'll tell you this, a lot of people have actually been interested in this and have been surprised. This doctor from Texas, he wrote to me and he said, I read Nightfall when I was a kid, and I don't normally read scientific papers, but I came across this and I was really happy to see this. I got a letter from a United States senator who said he's actually a physics professor, which is unusual in Illinois, I think it was. And he said, I enjoyed reading this. I'll use it in my classes. The American Physical Society, they put out a set of podcasts on things that they think are interesting. So they did a Skype interview with me and with Smaran, and you can find this 10-minute podcast on the APS site. So it's something that people actually are interested in. And so when I said, okay, when I saw that okay, maybe this has a broader interest, I thought I would put together a talk on that. So now the story details, and as I said, most of this comes from the book and not the short story. The short story ends with the world basically ending. The world ends in fire. The book goes on to the reconstruction of the world. But there's a lot more details in the book than the short story. And so this is set on this planet, Lagash, which orbits its star at a distance of 10 light minutes. The Earth is 8 light minutes from the Sun. So this is 1.2 times the distance of the Earth. There's 5 other stars in this system, Dovim, Tano, Siddha, Trey, and Patru, but no other stars are seen. And that's because at all times, one of these stars, at least one of these stars is in the sky. So there's never any darkness. There's always light. The main star is Onos. Of course, the world goes around Onos. So you have that star rises and sets as the planet rotates. But the other stars conspire so that there's at least always one in the sky, anywhere from 1 to 5. And this has been so for as long as people can remember. Now, because there's at least one star in the sky, the star is bright enough that no other stars are seen. So only these 5 stars. Now, you can imagine that the motions are quite complex. So it's not like our solar system, where all the planets go around the sun in a nice, easy manner. So as a result, the equivalent of the law of gravitation was only found about 20 years or so before the start of the story. So in one, they're excavating a burial, a mound, an old mound outside somewhere. And what they find is the layers. One civilization is built on top of the other civilization. And they find 9 such layers, each one separated by 2,049 years. So this is an odd thing, right? Everything is separated by exactly 2,049 years. At the same time, the astronomers, while they're looking at the motions of these stars, they find some small deviations from this ideal case of the law of gravitation. And so in trying to solve these issues, what they find is that there's a moon going around this planet Lagash. The moon is almost the same size as Lagash, almost the same mass. And it goes around such that once every 2,049 years, it causes an eclipse of Dovim, which at that time is the only star in the sky. So once every 2,049 years, you get this moon passing in front of the star, which is the only star in the sky. And so once in 2,049 years, you get a period of darkness. Okay, so that's when you see the stars. And then they do other things. They're all so used to light that there was an amusement park that opened, again, just at the beginning of the story. And it had a tunnel where people would go through and spend 10 minutes in absolute darkness. And some fraction of the people who went through that tunnel came out insane. They couldn't go inside anymore. They had to sleep out under the stars, or they were completely incapacitated. And so everything comes together, and then they find that once every 2,049 years. So they predict that in the next, I think it was 5 years or so, this eclipse would occur, and you would get the cycle of destruction. So now the challenge is to set up this system where you have you have this moon and planet, And every 2049 years, you get an eclipse of the only star in the sky. So that's the challenge. And Asimov himself, that wasn't the point of his story. He was not so concerned about whether this system was possible or not. He was more interested in exploring the sociological aspects. What would happen if you had one night of darkness every 2049 years? What would happen? So he set up some sort of system that may or may not have sounded okay, but he didn't worry too much about the details. And it's not fair to expect him to. And it's not, in that sense, it's not really fair of us to hold him to that standard. But then when I was a graduate student, there were no planets, no extrasolar planets at all. It wasn't till my final year of graduate study in 1986 that the first extrasolar planet was discovered. And since then, in the next 20, 30 years, by about 2000, there were another 200 or 300 planets discovered. Now, since the launch of the Kepler satellite, there have now been several thousand planets discovered. So I think the current count is something like 1,500 confirmed planets with another 3,000, 4,000 hypothesized planets, putative planets. And these planets and the planetary systems are all sorts of weird systems. Again, when I was a student, the solar system formation was pretty straightforward. We had the rocky planets near the sun. We had the cold Jupiter-type planets far away from the sun. Why is that? It's because when you're close to the sun, things are hot, and so all the hydrogen and all evaporates away, and so you can't have giant planets near the sun. But now, ever since Kepler, or perhaps even before Kepler, we've been finding all sorts of hot Jupiters. Jupiter-sized planets orbiting their star faster, or in orbits that are closer than Mercury. So this has become a real puzzle. How do these planets get there? And so this is one of these systems. This is Kepler 64, and this is a painting by Dirk Terrell. He's actually an astrophysicist, but he paints as his hobby. And so this is a painting that he made of this system, Kepler 64. And this is a system with five stars and a planet in a system of 5 stars. And he's postulated a moon going around one of those planets. And so this is what that system might look like from the moon of that planet. Of course, it's an artist's conception. So since Kepler, these systems really do exist. It's not just the writer's imagination. There really are systems where there's an immense amount of complexity. So then what we did is we looked and saw what are the things that we can extract from the book. What are the observables? What are the things we have to explain? After all, this is what astronomy is. We have observables, and we try to have theories to explain those observables. So as I said, the planet Lagash, where everyone lives, that orbits its star at a distance of 1.2 AU. That's 20% greater than the 10 light minutes away, 10 light minutes. That's, I guess, about 120 million kilometers. 2 of the stars, Trey and Patru, are a binary pair. The other 2 are Tano and Sita, are also a binary pair. These are white stars. And so we said that, okay, if they're white stars, well, then they have to be white dwarfs. They can't be main sequence stars like Sirius or Vega, because those stars would just be too bright for this system. So they have to be white dwarfs. So that said, that told us something about this. The more important star for our story is Dovim, and that's a red star. And so we said that this has to be a red dwarf, because again, if it's a red giant like Betelgeuse, it'll just be too bright. You can't have life on this system. So that defines the different stars for us. Then what we had to do was we had to try to define a set of orbits that would work out, that would give us a reasonable system. Before I go any further, I should just say that we did not do a complete simulation of the system. we basically did some hand-waving arguments to say, okay, what kind of system would work out. And okay, so this is the furthest system, the furthest star from Lagash is 110 light minutes away, which is just outside the orbit of Saturn. No other stars are visible, even though the system is at the edge of a globular cluster. So there's a whole bright set of stars there, but no other stars are visible. The crucial things for our work here is that this eclipse lasts over the entire rotation of the planet. If you look at a lunar eclipse, a solar eclipse on the Earth lasts for what, about 8 minutes at maximum? 6 minutes, 8 minutes, whatever it is. But here, it lasts for 9 to 14 hours. The reason it has to last that long is because the entire civilization all over the planet collapses, and so the whole planet has to have darkness. So that means this eclipse has to last long enough for the planet to rotate around under it. And one of the things that's given is that the diameter of this moon is 7 times that of Deauville at the time of eclipse. The moon is normally invisible, by the way. We don't worry about that. It's invisible for whatever reason. Okay. So we started with the star Deauville. And so the first thing we said is that the star has to be bright enough to blot out the nearby cluster. And I should say again that the purpose of this work was just to see how far we could go. What can we say that's realistic? In a sense, it was one of the reasons I did it was so that Smaran, who's now a graduate student in Germany, could get some experience in doing research. I mean, what the problem is immaterial. The fact is that you're still deducing theories that apply to facts. And so this star, Deauville, has to be bright enough to blot out the nearby cluster. It's an M-type star. Because it's an M-type star, we know what its brightness is. And this is true of any star. If you tell me the color of the star, I can tell you the brightness of the star for 95% of all stars. They're on the main sequence, and that's what the main sequence means. If I know the brightness, I know the spectral type. If I know the spectral type, M, G, whatever, F, I know how bright it is. And so this star has a brightness of 9. The distance of the star is 44 light minutes. If I compare with our own solar system, the apparent magnitude of the sun is minus 26.7. That's how bright the sun is in the sky. The faintest object we can see in the day is about minus 4. So the moon is perhaps a little brighter than that, minus 5 or minus 6 in the day. Venus is minus 2, 3, minus 4. Okay, so typically you can't see Venus in the day. There's a difference of about 22 magnitudes. And so we calculated how bright this, we just basically verified that this star would be bright enough to blot out the nearby stars. That was one thing that we did. Our main result was really in finding out some characteristics of the moon. Now, the angular diameter of the moon is 7 times that of Deauville, so that tells us that it's 26 arc minutes in diameter. Now, there's 2 ways that a thing can be, that an object can be big. Either it's close to you and small, or far away from you and big. Now, we know from Kepler's laws, or well, we know from any system, if you simply have a planet and a moon, now the planet and the moon are almost the same size, that's one of the things we know from the story. So we know that they have to go around their common center of mass. So there's different ways of doing it. This is one way. You can have them go near. They always have to be at the same distance. The center of mass doesn't move because of Newton's laws. There's no external force. So the center of mass is always fixed. So you know that the planets are always, or the planet and the moon are always directly opposite each other, and they have the same speed. So using Kepler's laws, we calculate the orbit. Now, but really you don't even have to do that much. You know that if the if the two are close together, then they're both moving fast. This is like a spacecraft or a comet. You know that when a comet goes near the sun, it speeds up, whips around the sun, and then goes off. As it's far away, it moves slowly. So the same thing happens here. If the two are close together, then they'll be moving fast relative to each other. And so it's very hard to have this 9-hour orbit, 9-hour eclipse. If they're far apart, then they're moving slowly with respect to each other. And so it's much easier to have this long orbit. Now, if the density of this moon, moon is close to that of our own moon, it'll be quite small. It'll be like our moon, like our own moon. And so because it's small and dense, it'll be moving much faster. So what we did was we calculated the density of the moon, the eclipse duration, as a function of the density of the moon. And what we found is that the density of the moon, in order to get these 6-7 hour eclipses, 9-hour eclipses, the density of the moon had to be close to that of Saturn, close to that of water. So you have a big light moon and you have a small, I don't know anything about the planet, but maybe it's a small rocky planet. So that was our main conclusion. The conclusion is that the moon has to be big and it's slow moving, otherwise you won't get the eclipse. Now later on, Smaran tried to do some simulation, but this was more just for the, just to get some practice doing it. And he wrote some programs he was learning Python at the time, so he wrote some programs in Python to do orbital simulations. And this is something he came up with. Now, this is actually more difficult than one might think. The problem is that if you're trying to trace the orbit of a planet for a long period of time, you do it normally by balancing forces. So you take a planet here, you calculate the instantaneous force from all the other bodies, and then you move you say force equals mass times acceleration. So you accelerate it by a little bit in whichever direction it's going. And then after a short time step, you then do that over and over. The longer your time step, the more you're approximating a circle by a series of straight lines. So at the extreme, if you have a very short, very long time step, you would go from here up to here, and then you would correct it. And so clearly, you're building up errors. So you want to have as short a time step as possible. If you have a very short time step, and you want to try to integrate the system over millions of years at time steps of a second, firstly, it takes forever to do it because there's 10 to the 8 seconds in a year, so 10 to the 14 seconds in a million years. So you take a long time, and even more, you start building up errors. So the real codes that do this, the codes that do real orbital simulations, are much more complex. They balance forces at each time, they recalculate angular momentums and so on. So this is just something that we came up with. I wouldn't take it seriously, but what we did find, so that is the one thing that we found, the thing that we stand by, that the moon has to be large and low density. So what we do in the future, I don't know. I mean, at some point you get into limited returns. How much time do you want to spend on this versus how much return you're going to get? And in many cases, we're limited by the lifetime of students. So students come for 1 month or 2 months. So it has to be something that's possible to do in 1 or 2 months. But ideally, what I'd like to do is to start with a better program to do simulations and really start visualizing what's going on. Now, I should just add that I keep an eye out for little problems like this. And so another problem that I have that I'll give a student this summer is that Herschel, William Herschel, who discovered Halley's Comet, who discovered Uranus, sorry, Halley discovered Halley's Comet, but William Herschel, who discovered Uranus, and incidentally wanted to name it George's star, because George the Third, I think it was paying his bills. So he thought he would name it after the person who's paying his salary. Other people didn't think that was such a great idea, especially in Europe. And so they named it Uranus, which after a century or so, the British also accepted. But another thing that he did was he looked up in the sky and he counted stars in different areas. And based on that, he came up with a model of the galaxy called Herschel's model. Because he didn't know about interstellar dust or different types of stars, he came out with a nice spherical galaxy. It's actually a wolf-shaped galaxy, a fairly odd shape with the sun at the center. And so this is something that's easy to do now. You look at with a modern star catalog, and again, just count stars in the sky and see what you get. So these are the kind of projects. Someone suggested that we look at Larry Niven's Ring World, where he has this Dyson sphere around. This is a type 3 civilization where you capture the entire output of the star. So you put a sphere around the star and you capture all the output for your civilization. So he suggested doing something like that. But that's in the future. And so what I'll do is I'll end with this quote from Asimov. And this is something that applies particularly to students, but really to everyone. And so because we all have a tendency to say that this is what we think, and so everyone else thinks like that also. And so what he said is, so the universe is not quite as you thought it was. You'd better rearrange your beliefs then, because you certainly can't rearrange the universe. So let me stop there, and I can take questions if